Hi, good afternoon, everyone. This is Mauricio Hansich and Claudia Rosas here in BSc. Today we will tell you something about a successful interaction that we had in ChEESE and Bob. And for doing that, what we will do is start by telling you what the Center of Excellence is. I don't know if everyone in the audience knows what we are talking about. What is ChEESE specifically? In ChEESE, we use some codes that we call flagship codes, and one among them is for 3D. And everything about what is in the outline will be explained through the presentation. So where is the Center of Excellence? Well, Center of Excellence is like a regular European project, an H2020 project, but with some specific with a specific orientation. Let's say it's really devoted to high performance computing, but also associated to a specific field of technology. So there are many Center of Excellence. There are around 9 now, and more are coming probably in a following call. But currently, what we have is this. We have Center of Excellence for like BioAxle, that is Center of Excellence for molecular dynamics. We have another one that is CombioMed, that is Center of Excellence for medicine. We have one for materials, that is MAX, now in its second edition. We have EasyWays 2 for climate, CoE for energy, Hidalgo for big data, and Accelerate for engineering applications. And transversal to all of them, this is the POP Center of Excellence. And why is that? Because every single Center of Excellence here is somehow related to high performance computing and high performance applications. So POP providing support for enhancing high performance applications makes sense to collaborate to every single Center of Excellence here. We particularly came from ChEESE, that is the Center of Excellence for solid Earth. Okay, so what is ChEESE? ChEESE is a new initiative in the sense that is a Center of Excellence that appeared in this last call. Many Center of Excellence exist now for the second iteration of the project. ChEESE is not in that case. ChEESE is the first stage of a Center of Excellence and is devoted to solid Earth. That means everything that is related to what happens in the Earth internals, okay, or related to that somehow. For example, volcanic activity, or earthquakes, or tsunamis. These kind of things are the things that we are trying to tackle from ChEESE and trying to provide some impact, real impact on society from the Center of Excellence. The consortium is built upon many different partners from abroad in Europe. We have a budget of over 7.5 million euros. We have 42 deliverables. There are many peer-reviewed publications. Here only 5 because this is the official version that we have in the web page, but I can tell you there is something like 2 or 3 times that amount already in just 10 months of the project. We have 42 deliverables, 12 partners from 7 different countries. We are scheduled for 18 different international events, and the project will last 36 months until the end of October in 2021. The most important thing from ChEESE is what is highlighted here. There are the 12 pilot demonstrators and the 10 flagship codes. The important thing from ChEESE is we are trying to develop different pilots for things related to solid Earth, using for developing that flagship codes, flagship high performance computing codes. Okay, and the important thing here is that some of those pilots should end up being some kind of service for the society. Okay, so regarding the structure of the Center of Excellence, what we have is, besides Work Package 1 and 6 for management and dissemination respectively, we have the more technical work packages in the middle that are Work Package 2, devoted to enhancing the flagship codes. We have Work Package 3 that is devoted to building workflows around those applications that we use in Work Package 2, because for building a pilot, you need more than the high performance computing application. You need to move data from some place to another, translate things, try to figure out when a specific event occurs. All of this is bigger than the high performance computing application itself, and is built upon the workflows and the tools. With those, we will develop the pilots, and some of those pilots from Work Package 4 will end up being services in Work Package 5. So more or less, what we have is Work Package 2 providing the applications, 3 the workflows. Both things together are used for building up the pilot, and now we will see what they are. And finally, some of them, those that has a proper maturity level, a proper technology readiness level, the TRL is up to 7 or 8, will be pilots for services, actually. But today we are here from Work Package 2, because at Work Package 2 is where flagship applications are being handled and are being enhanced and are being worked with, jointly with vendors and researchers. And among those flagship codes, we have level 1 codes, level 2, and level 3. Level 1 are those applications that are pretty much mature in the sense of scalability and efficiency. They're in the order of the petascale already, and we are trying to move them to the exascale. Level 2 are applications that are in the pre-petascale state, so we expect up to some thousands of cores in scalability. And then there is level 3 applications. There are applications that are a bit immature in the sense of scalability and efficiency, and we are devoting a lot of efforts to those kind of applications to try to move it higher in this scale that we define. So this table more or less summarizes what we do in ChEESE, because it's a table that shows where are the pilots that we are developing. Remember that we said that we have 12 pilots that are on the columns, and we have 10 applications that are on the rows. The colors are the level of the applications. Green ones are level 1, yellow ones are level 2, and the pink one are level 3. Okay, so related to pilots, we can say that we are working in pilot 1, 2, and 12 for urgent computing, that is using high-performance computing resources in a crisis situation. For example, if there is an earthquake somewhere, what we do from ChEESE is define the policies and the workflows needed for using a high-performance computing environment with a really, really high priority. Then we have other pilots like 5, 6, and 7 that are useful for hazard assessments. These are pilots devoted to try to produce information about how critical a specific hazard could be to a specific zone. Then there is PVA, that is the pilot A for early warning systems for tsunamis. Okay, the letters in parentheses are seismic for earthquakes, T for tsunamis, and V for volcanic. In this case, PD8 is for tsunamis, and what we are trying to do here is whenever there is some event that is detected that is prone to produce some kind of tsunami somewhere, then the early warning system try to figure out the level of risk about that and produce information faster than the tsunami may reach a specific coast. Then we have another for big data in PD10 for earthquakes, also for doing some kind of assessment for seismic situations, but based on big data. And then there are some others like PD3, 4, and 11 that are devoted to different unrelated things like the ones I was talking about. Okay, so we're here not only to speak about ChEESE, but also or most important, to speak about our experience in working with POP from ChEESE. Okay, we have 10 applications. In the month of July, we had a deliverable for explaining the current situation of the application, that is, which is the actual efficiency of them. So when we start the project, we contact POP and we talk between each other if it's a good idea to produce everything that is related to audits and analysis for the applications from POP. Why is that? Because we have applications with really different level of maturity, and POPs provides us with an homogeneous way of producing information about the behavior of the applications. So we can produce information that is more or less standard and homogeneous through the whole Center of Excellence with a single methodology. And for that, and for us, this was a good idea. And so we talked to POP and we actually did it. So in the columns, we have who was the partner either in POP or in ChEESE that did the analysis, because in some cases we have some applications that were proprietary or the developers want to do the tracing by themselves, or for whatever reason, some of the developers in ChEESE did the tracing and then POP produces the actual audit from them, or some of the analysis for some other applications were done by POP from the start to the end. Okay, you can see where those things were run. You can see that there are many different high-performance computing centers and environments involved in providing resources for producing these audits. And in the last column, you see a really summarized conclusion of what we get from POP for different applications. In this talk, we will center our focus on Fault 3D. Fault 3D is an application for volcanic eruptions, for modeling the dispersion of an ash cloud from a volcanic eruption. And we did the audit for Fault 3D at BSC, okay, and running things in Mare Nostrum 4.
So what's Fault 3D? When it started, it was classified as a level 3 application. So we're pushing and moving forward this application to closer to the exascale and petascale first and exascale later. So Fault 3D, what is an open source software that simulates how the particles move around the atmosphere. It's not young. It's a code that started developed in 2003. So it has more than 15 years of development, and by the time ChEESE started, it was in the 7th version. And within ChEESE, we implemented from scratch the version 8. So we will be talking about version 7 and 8 along the following slides. Version 7 was the point of start before ChEESE. So it relied only on atmospheric dispersal of particles, while version 8 also considers aerosols and radionuclides. Version 7 had only one model to simulate the particles movement. and version 8 considers two different schemes, one with the same computational cost and another less, with the same precision but less costly. Version 7 had initial parallelization of particles that take as a reference the better use of the memory, while version 8 it's trying to extend as much cores and processors are available. So this first idea had to be rethinked. And now the I/O is considered to be parallel to avoid bottlenecks when writing and reading to disk. Our interaction with POP started about the month 6 of the ChEESE. This is about around April, May. So we provided the version 8 of All3D to POP, and they proceed to perform the first audit. The solution, the result of this audit was to take a look at the communication and computational ratio, because the executions produced traces really big, and it was caused by the number of communication that were performed. They were really tiny, really with fine grain. So our first step was to take a look at that. So by month 10, more or less, we started working on these optimizations here in BSc, and we started taking the first initial measurements. Of course, the second round of performance audits for all the 10 flagship codes will be carried out in between month 19 and 27 of ChEESE. So the idea is, once all the codes, not only for 3D, but all the 10 flagship codes go through to this second round, they will have an okay from POP expert that we actually achieve a really good efficiency and scalability with the enhancements. And of course, we reach an upper level in the classification. So the main message from POP was to look at the computational and communicational ratio. So what we did was to take a look at how the initial version of All3D 8 was communicating. Actually, the values are mapped in a 3D space, and in this graph we try to depict what will be the decomposition within two nodes, one on the left and one on the right, and then the new approach on the far right of the screen. So the older version, or the without improvement version of All3D, is completely on the left, and it was needed at every single step to communicate all the particles. So you can imagine how these small and tiny green and purple cubes were communicated within the two processors every time a computational step was carried out. This idea was proposed like this initially because it reduced the number of accesses to memory. So it was intended to pursue a very efficient memory access, but that works well when you're working in a single processor. When you're adding more levels of parallelism, this becomes a huge bottleneck, because there are a lot of messages, tiny messages flying around the network. So the modification that was introduced by BSc in All3D 8 was what we see on the far right. Now the boundaries that are touching between the two processors are computed with all the steps. You compute all the 4 steps for the values on the boundary, and then you share the information, and then you continue with the rest of the calculations. Only by doing this, we obtained a higher communication ratio. We had to rearrange some data to align with these computing dimensions. Of course, by doing this, we reduced the decision statements in the iterative code region. We removed memory allocations, and of course, it gave us the opportunity to use a different solver, in this case, Euler, a first-degree Euler. In this graph, now you can see the ideal speed up for a strong scaling execution, where we reach with Fall 3D version 7 and where we're reaching with Fall 3D version 8, Runge-Kutta 4. So it was the first implementation, the very fair comparison between the two codes. As a first highlight, Fall 3D version 7 was enabled to go beyond 100 CPUs. Now we can easily go above the thousands without any trouble. By adding the Euler solver, we used the same amount of resources, sacrificing a bit of precision. So now the computations are order 1, and this enables us to have a really high speed up ratio in comparison with the version 7 that was the legacy code where we started. So you can see that with 1 and 2 CPUs, version 7 still better because of this optimization they had in the memory allocation. But once you start adding CPUs, actually by using only 8 CPUs, now version 8, it starts almost doubling the performance. And by 64 GPUs, it goes up to 4x of speed up in comparison with the older version. We don't have this graph with more CPUs because, as I stated before, it's impossible to run version 7 beyond 100 processors. Another interesting thing is that by adding the Runge-Kutta 4 and the Euler, now we have a model that is less over diffusive. If you're looking on the graph on the left, it's version 7, and there's an area painted in yellow that shouldn't be there. It's not true. Those are particles that shouldn't be there. So now we have more precise simulations, and we are able to scale really, really high. So the next steps regarding Full 3D. In last year, there will be another performance audit, so we are willing to go to the more than 2,000 CPUs, and of course, continue improving scalability and efficiency. Currently, they are testing some asynchronous communication to try to improve the performance a bit more. And of course, the current performance of the code is under review. Is actually one publication that is under review. So we are really happy with these results. Next steps within ChEESE. Well, in month 27, we are looking to have another interaction with POP to have the health check to all the 10 flagship codes, and of course to see if we were able to actually reach better levels of scalability and efficiency from all of them. Of course, we are promoting the successful interaction with POP as a transversal CoE. And one use case is that we are already using this interaction with some other H2020 projects as an Enerxico. And our take-home message is that performance optimizations following POP's methodology for HPC codes has not only proven to be efficiency in both time and use of resources, because everything is centralized with the experts. It's also very useful for the scientific software developers. Developers can now have a broader view of how their codes are behaving. Some of them can actually read the graphical representation that POP generates and understand what's going on in their codes. And of course, this interaction has proven to be successful, not only within European CoEs, but it's also being exported to international projects with strong participation in Latin America. We had 2 years ago HPC for Energy, and this year Enerxico. So POP is moving around Europe and beyond. So thank you very much for your attention.
Thank you.
Now we're open to questions. Yes, we have one question from the registration portal. They said, how do I get involved?
Yeah, we actually didn't understand the question. So if the one producing it is able to elaborate a bit more, maybe we can answer that. If anyone else also has some more questions, we are eager to try and answer them.
I don't know if I can show this. No. Wait. I don't know how to open this now, I think.
Sorry, John, we are trying to see the questions. Ah, now we got it.
Okay.
Okay, John, we have another question from John. It's clear from the presentation that POP makes a difference for Fall 3D, and there is a question: did it make a difference for some other flagship codes? And the answer is sure. We extract useful hints for every single application we put through POP for doing the analysis. Remember that we showed a table here. I'll get it eventually. Here with the conclusions for every single application that we have in ChEESE and went through POP. The hints were really useful. I know that there are, for example, a case for another volcanic related application that has a similar problem that we have found out in 4.3D, but related to input, output, and communication and entanglement. There are many different things there that went through POP and came to the light. Okay, now they are fixing it. So POP people is actually working today with people from ASHI, I think, for figuring out how to solve other things that what we find out through the audit process. For other applications, we find I/O inefficiencies or that the hybrid performance has some issues when we are moving data around from MPI processes, or we are not using as much as we can the information in shared memory or OpenMP. So yes, the answer is yes. Every single application in POP in ChEESE has a benefit from using POP to get information about the application themselves. For sure, the applications in level 3 were the most those applications that benefit the most from POP, but even the level 1 and level 2 get a really good feedback and useful feedback for improving the application.
And we have another one.
Yeah.
Do you need to be part of a CoE to use POP? No, you don't need to. If you are a developer, a researcher, a university, and you have some code, a good candidate to go into HPC, or you're having some parallel computational hours allocated, so you can go through the POP webpage and ask for a service, and depending on the characteristic of your code, they will handle out to the corresponding expert. So no, you don't need to be a part of a CoE to use POP. Okay,
there seem to be no more questions, so thanks everyone for attending our talk. And if you have more questions in the future, you will get the slides, and you have the mail addresses for Claudia and myself there. So please feel free to contact us if you have any other doubt about our relation between ChEESE and POP. Thank you.
Thank you.